In this video, we're going to investigate an element of the Lagrange multiplier process that we haven't really looked at, and that's the interpretation of that lambda value. When we started, we simply used it as an indicator that the two gradient vectors are parallel, because two vectors are parallel if they are a constant multiple of each other. A natural follow-up question, though, is does that lambda have any meaning in the problems? And it turns out it does have a nice, elegant interpretation, especially when we're looking at applied problems. To study the value of lambda, what it means, it's going to turn out to be important to look at magnitudes rather than the raw vectors themselves. Specifically, we can look at the gradient of f and its magnitude, representing the rate of increase of f if we take a step in the direction of its gradient. And likewise, the magnitude of the gradient g is the rate of increase of g that we would see, again, if we took a step in the direction of the gradient. Well, if we take a step in the direction of the gradient at our interesting points, the ones coming out of Lagrange multipliers, these directions are the same at our solution to the Lagrange multiplier equations. So that's interesting. It means we can recast this by taking the magnitudes of everything here. And if we solve for lambda, it'll be an absolute value because we've taken magnitudes of everything. But this lambda somehow captures the rate of increase of f divided by the rate of increase of g. So that's an interesting reformulation, but not necessarily enlightening quite yet. Here are a couple of ways to recast that. Lambda gives the rate of increase of f divided by our rate of increase of g, and that is the value on the constraint. In particular, g of xy equals k. That k value is the value of our constraint, and what we're asking here is if we increase k by a little bit, what do we get in terms of a change in f? Well, that actually sounds a lot like a derivative. It's the derivative of our function f relative to this constraint value k. Another way to say that more colloquially is that lambda gives the value of the approximate increase in the value of f when we increase it by 1. So this can often make more sense in the context of an application. Let's consider f of xy to be the output of a factory in numbers of units shipped, and our constraint is the manager's budget. So k is equal to the dollars and thousands that the manager is allowed to spend. They find the best values for x and y using Lagrange multipliers, and then they find that lambda is equal to 29. They do some calculations, they get xy, and then they can go back and solve for lambda. Well, lambda, an absolute value, is that ratio of the gradient of f over the gradient of g, and we can think of that as a change in f over a change in g, and we're saying that that's 29, so it's approximate. So what we're saying here is we can increase the number of units shipped by around 29 if we increase the budget by 1. And what are the units there? Thousands of dollars, $1,000. Another way to rewrite that is the change of f is approximately here too as well, 29 times the change in g. So if we make the change in g 1, then our change in f is 29 units, and it also scales up. If we had an increase in budget of $2,000, we would use 2 for here, and we get twice as big a change, or 2 times 29, as our change in the output. So it really ties in what would happen if we changed the problem. All the way through the Lagrange multiplier equation calculations, we assume the constraint is what it is and when it's fixed. But this is a nice what-if extension, which is we found our optimal thing for our current budget, but what if our budget was a little bit bigger? What bang for our buck would we get out of this calculation? This indicates that the lambda value is not just an abstract quantity representing a filler piece capturing the parallel nature of these two vectors, it actually has a follow-up interpretation that can be important in some applications.